Hello everyone, thanks for coming. So my name is Branimir Rusanov, and today I'll be presenting to you my project that I've been doing over the last year. The title is Cone Beam CT Intensity Correction, a convolutional neural network approach for correcting head and neck scans. And I would like to introduce my supervisors, Mahsheed, Martin, and Godfrey, who come in if you would like. Yeah. Okay, so what are the aims? Well, as a proof of concept, this study aims to demonstrate how deep learning methods can be used to improve CBCT image quality and HU accuracy. And in particular, this is a problem for cone beam CTs because of the inherent geometry of the cone. You acquire the entire patient anatomy in one rotation. Therefore, more geometry of the patient is being intercepted by the cone beam X-rays, and as well, the detector is larger compared to a fan beam CT, which is standardly used for diagnostic imaging, and therefore more scattered X-rays can be detected. And this severely impacts and degrades the image quality of the subsequent reconstructed CBCT. And successful implementation will bring us closer to daily dose accumulation monitoring, and as well as adaptive radiotherapy. So what are the methods and materials? So I used a modified version of the a priori scatter correction algorithm to serve as the central method for cone beam CT scatter correction, and this method is taken from the literature. In short, the method uses prior information from CT images to estimate the scatter signal in the raw cone beam projections. And I think it's worthwhile to outline the method before we proceed. So step one, we acquire the CT and CBCT images plus the raw cone beam projections that come from the Varian cone beam system. And for this particular study, I used 4 phantoms. So we used a thorax phantom, a pelvis phantom, and 2 head phantoms. Step 2, we rigidly register the CT to the CBCT coordinate system such that we have the same pixel spacing and origin. And this is done through slicer, but it's kind of a trivial operation. Step 3, using the registered CT image, we perform a forward projection to simulate what the CT raw projections would look like as cone beam projections. And the simulated projections serve as scatter-free approximations of the CBCT projections. Now this step is very important because for some of you who may not know what forward projection is, it's the reverse of back projection, where with back projection you take your measured attenuation signals and you apply, you essentially smear them out along every angle in order to get your reconstructed image slice by slice. We essentially do the opposite for forward projection. And to do this, we use RTK, which stands for the Reconstruction Toolkit. It is an open source software specializing in cone beam reconstructions. We use the cone beam geometry, which is it's an XML file that comes bundled with the Varian raw cone beam projections. And we use the registered CT in order to simulate what the virtual CT projection would be like. And of course, we say there's no scatter because the registered CT is of diagnostic quality, and it already has algorithms post-reconstruction that remove scatter, so then when we forward project it back into the projection domain, it does not have any scatter signals. Step 4, the raw cone beam projections come in units of intensity from the Varian CBCT machine. So we need to normalize them by taking a blank scan measurement, and this is the Beer-Lambert law. We essentially just divide both sides by the blank scan measurement in order to normalize. And furthermore, by normalizing, we also remove the attenuation profiles seen here on the left and right that are caused by the bow tie filters on that are present in the cone beam source. Step 5, the simulated CT projections, these come in normalized attenuation units. So similarly, we rearrange the Beer-Lambert law to get it in this form, which is the same, so that it's in the same units as our raw measured cone beam projections. And in step 6, we subtract these simulated CT projections from the CBCT raw projections in order to get the difference image, which contains all of the intensity deviations. We then apply a smoothing filter to extract the low frequency signal that pertains to scatter. And in this case, the smoothing filter that I took from the literature that's been optimized in the literature, and this consists of a 51 by 51 median filter followed by a 71 by 71 Gaussian filter. And in equation form, this is what I have just described. And we should note that the smoothing not only extracts the low frequency scatter signal, but it also corrects for minor misalignments which may be present between the CT and CBCT dataset. This is especially important if you're using patient data, because inevitably, even after deformable image registration, you have small misalignments in the projection domain. So the smoothing takes care of those misalignments. In step 7, we subtract the scatter-only signal from the CBCT projections in order to get the corrected projections. And essentially this is what is done. And finally, in step 8, the corrected CBCT projections are reconstructed using the FDK algorithm in RTK. And here I'm kind of showing pictorially what all the various stages look like. So in A, we have the blank scan. In B, we have the raw cone beam projection. In C, we have the normalized cone beam projection, and we notice that we don't have those attenuation bands. In D, we have the virtual CT projection. In E, we've subtracted the virtual CT projection in order to get the residual signal. And in F, we've applied a smoothing function in order to extract the scatter signal. Okay, now moving on to the machine learning aspect of this project. So there's a lot of similarities with the a priori method I just discussed, but also some stark differences. So once again, we begin with our phantom data. We take a cone beam CT as well as a planning CT of the phantoms. We reconstruct the cone beam CT, and we use that to rigidly register the CT so that we are working in the same coordinate system just as before. Then using the registered CT, we forward project in order to get the virtual CT projections, and then subtract them from the raw cone beam projections in order to get the estimated intensity deviations. And up to this point, this is the same as what I've just described. However, we do not apply any smoothing to these estimated intensity deviations. And now we introduce a machine learning architecture called a UNet, which came out in 2015, and it's specialized in medical image segmentation as well as using small data sets, but it's been modified to work with regression instead of classification kind of problems, because here I'm predicting real world values instead of ones and zeros, which is what a classification task is. So what we do is that we set our training input to be the raw cone beam projection that it's fed into the UNet in the training phase. And then we set the target that it's trying to predict as the estimated intensity deviation. So this consists of the 4 phantoms, around 2,000 projection images that it's been trained on. So once the model's been trained, we then input raw cone beam projections, but of patient data. And the UNet will predict the subsequent intensity deviations for those patient projections, but they will be perfectly anatomically aligned. And this is the benefit of using this method, as you will learn later on. Then once we have that output, we subtract it from the raw cone beam projections to get a corrected cone beam projection, which we then can reconstruct in order to get our corrected CBCT image. So this is the model, the UNet model. It's called ScatterNet, which is the modified version of the UNet. And it was introduced by Hansen and colleagues in 2019. They used it for a similar task, a little bit different though. So essentially what happens I won't go too in depth because this will take hours and hours, but essentially the raw cone beam projection is input, and the encoder path is, the image travels along the encoder path. Along every single block inside there are many convolution kernels, each having thousands and overall millions of learnable parameters. So essentially what happens is matrix multiplication between the input image and the various filters or kernels contained inside every block. The output of every layer is seen next to the, sorry, I should clarify. What happens is that as the image flows down through the encoder path, we compress the information or the features stored in the input into a smaller and smaller physical dimension, but we produce more and more feature maps which contain the various extracted features from the original input. So the numbers next to every line, next to every arrow, correspond to the number of output feature maps. So down here we're going to have 256 of these very, very small spatially dimensioned features. And then the decoder path does the opposite. We unpack that information and we retrieve our input physical dimension. However, we collapse these feature maps into a single dimension as matching our input. Except we don't retrieve our raw cone beam projection, but we retrieve our predicted intensity deviation. And essentially, this is performed through an iterative process where you compare the predicted intensity deviation versus what it should be. You use a loss function, in this case, mean absolute loss function, which is constantly compared, and the values iteratively updated in order to get the model to predict as close as it can to what the target should be. So I tested a total of 13 models based on the scatter net that I just described. SN0 is the base model from the literature. SN1, as you can see, I've increased the number of feature map outputs. Various modifications were made to SN1, such as including dropout in the architecture. I removed the convert block, which is specific to this architecture. I used mean squared error as a loss function. I decided to omit the pelvis phantom during the training phase to see what effect that had. I used no augmentation. I also used 180-degree augmentations. With SN2, I increased the depth of the model to 7 layers from 6 layers. SN4 increased it again to 8 layers, and I also investigated simpler models for SN5 and 6 with 5 and 4 layers respectively. And unless otherwise stated, I should mention that the MAE loss function was used, as well as random vertical and horizontal flips for image augmentation. So what are the results? So this table shows the reconstructed, so I took the best model, I fed the patient data, and I reconstructed the output. I corrected the projections and I reconstructed the output corrected projections. And this is the mean absolute error versus the CT ground truth, which was deformed to match the CBCT anatomy. So this is in reconstruction space, and this is working in projection space. So immediately we noticed that SN1 had the lowest MAE in RMSE, and therefore this was chosen as the best model going forward. We also noticed that predicting residual projections was more effective than predicting corrected projections, because I actually ran this model in 2 different ways. So I decided I trained it to predict the residual, and I also trained it to predict the corrected projection, which in this case was just the virtual CT. And the literature also corroborates this finding that predicting for the residual is a little bit more efficacious, which is what I also found. Simpler models performed worse. For example, SN2 and 4. SN2 and 4 did not perform, simpler models. SN5 and 6 performed much worse than SN1. And more complex models did not really show much of an improvement over SN1. And therefore, we can say that optimal model complexity was found. And similarly, using the dropout and the various hyperparameter changes did not result in any improvement of the model. In fact, it severely degraded model results. For example, no image augmentation for SN5-1. We get 101 MAE, which is almost double that of SN1. So you can see the value of including stuff like image augmentation. So on to the results. Here, on the left-hand side, I've demonstrated a line profile through a residual projection. So on the bottom, we have the ML predicted residual projection for the patient. And on the top, I have generated the same residual projection using the a priori method, because I also happen to have the corresponding CT images. Therefore, I could apply the a priori method and compare it against the machine learning method. And what we notice is that the magnitude of the ML corrected method matches that of the a priori generated scatter map, so that the ML approach is actually accurately learning to predict the patient intensity deviations while being trained on phantom data. And this is actually a novelty in the literature. But furthermore, if we look at the fidelity of these bumps, we see that the ML approach generates more precise residual projections. And this is because, again, it's been trained on phantom data, and meaning we don't need to consider any anatomical misalignments and apply any smoothing. Next, here I'm showing again a line profile, but through a corrected CBCT projection, cone beam projection. In black, we have the ground truth, which I've taken as the virtual CT. In blue, I have the uncorrected CBCT. In red is the a priori method, and in light blue is the ML corrected method. So as expected, the uncorrected projection has the highest signal due to scatter. Both the a priori and ML corrected methods follow the trend quite well of the CT virtual projection. And this again corroborates the finding that the machine learning method can correct cone beam projections accurately. If it's not perfect, for example, here it's underestimated the intensity, and here it's overestimated the intensity, but this is just a byproduct of the fact that I've trained on 4 phantoms, and it's a machine learning approach. It's not deterministic. There's always going to be some errors involved with it, but it's performing quite well, as you can see by how well it's fitting to those lines. Here, I have now moved on to the reconstruction. So I've reconstructed all of the corrected images for SN1, and the top table shows the MAE, the mean absolute error, and the root mean squared error for the various reconstruction methods. And what we notice immediately is that the lowest MAE in RMSE is found for the ML corrected method with 54 and 125 respectively, versus the a priori method, which had 58 and 138 MA in RMSE respectively, and the variant reconstruction had 57 and 148 MA respectively. So the machine learning method is outperforming both the a priori method and the variant reconstruction, which is great. Next, looking at this table, I also decided to look into specific HU regions and see how the MAE varies for those regions, so which method performs better against the others. And we noticed for the fat and soft tissue regions, they perform quite equally, all of the three correction methods. However, for bone, the ML corrected method is superior. And this is because the a priori method, it turns out it had excess smoothing. So what happens is that between regions of high gradient, such as bone and soft tissue, when you apply the smoothing in the projection domain, what happens, or too much smoothing in the projection domain, I should say, when you reconstruct, there tends to be the smearing of the HU across the soft tissue and the bone, so you get a reduction in the bone, as you'll see later, and this leads to a high MAE. Similarly, the variant reconstruction just tends to overestimate the bone. That's just, they don't really release much information as to the reconstruction method, but it tends to overestimate it. But looking at these values, you may think, wow, these are huge errors here, 93, 58. But we should take these values with a grain of salt because there is an intrinsic misalignment between the ground truth CT and the CBCT. So it kind of serves as a relative comparison instead of an absolute comparison, but I still think there's value in doing this analysis because all of the CBCT images have the same, they suffer from the same anatomical misalignment, and therefore it does give something, it does provide something valuable to us to see which method performs better. More absolute measurements can be considered when we consider the signal to noise ratio and the contrast to noise ratio. So on the right hand side here, I've displayed on the top row is the ML corrected, then we have the a priori method, uncorrected, and the variant reconstructions. And of course the ground truth CT on the bottom. And I've used these regions of interest to form the signal to noise ratio and contrast to noise ratio metrics. So what we notice is that, again, the machine learning corrected method has the highest signal to noise and contrast to noise ratio versus the a priori method and the variant method. And the reason for this is, I should actually say a little bit about how the scatter correction works in the variant reconstruction. So they use a pencil beam kernel to estimate the scatter signal. And they apply this on the raw, or they may even apply some noise reduction, but they apply it on the raw cone beam projection. But the thing is that projection is very noisy as it is. Therefore, by trying to predict the scatter on the raw cone beam projection, they kind of they're carrying through that noise into the reconstructed image. Whereas the a priori method estimates scatter signals independent of the raw cone beam projection. So that's why it has an improved SNR and CNR. But if we notice, the machine learning method is improved even over the a priori method. So what I actually found out was that not only does the machine learning method correct for intensity deviations, it also manages to denoise the raw projections. And this is an added benefit of using a convolutional neural network, which actually discovers labels on its own. And the label that in this case was discovered was the noise. And if I go back very quickly to you can't really see it here, but if you look at the air region, there's little dots everywhere which correspond to the noise. So obviously the neural network is correcting for that noise, which isn't present in the virtual CT projections. Okay, moving on. Here I have generated some line profiles through reconstructed images for 4 typical patient slices. In black is the ground truth again for the CT. In red is the variant reconstruction. And what immediately you can notice is that the variant reconstruction tends to overestimate the HU for bone. Here we can see in the bone. And it also slightly overestimates the HU for soft tissue as well. And it's also quite noisy, as you can see by the high amplitude of the spikes. The uncorrected reconstruction has the highest signal, again due to scatter. In orange we have the a priori method, which performs quite well on soft tissue. You can barely even see it because it matches the soft tissue region quite well, but it underperforms in the bony regions, especially here. You can see it's vastly underestimating the HU of bone, again because of that excess smoothing that I mentioned before. And the machine learning corrected method, it does not have this problem. It tends to estimate bone quite well. Really only here it's kind of underestimating it, but it performs very well on bone as previously mentioned. In general, it also performs quite well on soft tissue and not very noisy. However, it's not perfect. If we look at patient 2, line profile 1, it's kind of overestimated the HU into the same region as the variant reconstruction. And again, this is because the machine learning method isn't perfect. It can definitely be improved, but yeah, it's not deterministic. It's just sometimes you don't know why the results are this way, essentially. But that's the black box of machine learning. Anyway, and moving on to the difference images that I generated. So I took the CT and subtracted the various reconstruction methods. These two are the a priori method. We have the ML corrected method. We have the variant reconstruction here and the uncorrected reconstruction here. So immediately what you see is that what I was talking about, the red represents a overestimation of HU. So we see the HU from bone and the jaw kind of spilling into the soft tissue region, and this is again due to the excess smoothing applied. But in general, the soft tissue for the a priori method is quite good. There are regions of red and blue, but overall there's a lot of regions of white, especially when you compare it to the variant reconstruction, which has this red haze all over the place, which just means that it's overestimating the HU in general. The machine learning corrected method, on the other hand, it does not suffer from the same effect here around the bone region. And we also noticed that the direction of the error in the a priori method is similar to that of the direction of error in the machine learning method is similar to that of the a priori method, but slightly more pronounced. And this makes sense because both the methods use the same underlying, concept to correct for the scatter, but because it is a machine learning prediction, it's very unlikely that it'll be as good as having that raw data. But it's performed pretty well. Obviously, there's regions of blue here, but in general, it's performed pretty well, especially compared to the variant reconstruction. So in conclusion, as a proof of concept, the work has successfully demonstrated that cone beam CT raw projections can be effectively corrected for intensity deviations using deep learning models. The ML corrected image shows improved HU accuracy and image quality metrics over the variant reconstruction and the a priori correction method. And what are the advantages? Well, no prior CT information is required once the model has been trained. You can't do this with the a priori method, as you always need that CT information. No smoothing of the residual projections is necessary since the predicted residuals are perfectly aligned to the patient anatomy, and this is again something not possible in the a priori approach. The ML approach can actively estimate intensity deviations and denoise the CBCT projections, which is something I did not consider at the beginning of this project, but was a welcome addition. And the machine learning correction method takes around 1 minute to predict the residual projections, correct and then reconstruct the CBCTs, making it fast and reliable for the clinical workflow. It just hasn't been compiled in a kind of succinct workflow as of yet. And what are the novelties? Well, for the first time, a deep learning model was trained on phantom data to predict patient data and accurately estimate the intensity deviations. And as well, this work builds on the model proposed by Hansen and colleagues and improves it by investigating the different hyperparameters and tweaks to the architecture. They had very little discussion on what they did in their paper, so I'm pretty sure this is a lot more thorough. And I'd like to thank all of these people, Mahsheed, Martin, Godfrey, Pedjamin, and Mubasha, who took many hours of their day to help me, motivate me, and just give me tips along the way. So thank you very much, and thanks for listening, everyone.
It's a very interesting talk, really. But I just want to understand, absorb it. How can we use this clinically? I mean, in our clinic, for example.
Yeah. Like I said, the code is, I'm using Google Colab, I'm using Python locally, and I'm using RTK, so 3 completely different environments to get it all working. Ideally, you would have to streamline this and get it working all in one effective manner, which may incur some challenges. I know there are groups that are using similar methods. They've actually integrated it into their workstations, and they actively use the neural network to estimate the intensity deviations and then correct on the fly. So it is possible, but it would require a lot of kind of effort to get it working without, you just click a button and it outputs kind of the reconstructed CBCT. There's a lot of work in that respect, but it can be done. Yeah. in the projection domain, or?
Yeah, in projection.
Well, typically, the other kinds of intensity deviations are from the flat panel detector. It may not be uniform. And in the a priori method without machine learning methods, that is corrected for, because when you subtract the two, the no scatter signal versus the virtual CT from the raw cone beam projection, that's automatically accounted for. With the machine learning method, I guess because I'm not sure if there's any of these flat panel detector non-uniformities present in any of my data, so I don't know. And it'd be very hard to actually teach a model, because if you use it on a different flat panel detector, you don't know on that day or 2 weeks later, is it going to perform the same? It's not predictable, it's not consistent, and so therefore, I guess that is a limitation. But in general, scatter is by far the most deleterious feature for cone beam reconstructions, and it manages to handle it pretty well with just 4 phantoms, which I thought was pretty good.
Application of this method in adaptive radiotherapy.
Yeah, well, it's performing slightly better than the variant reconstruction. I would like it to perform even better, of course. And then you can begin to consider replanning on the day of the patient's treatment. I would like to extend the study, ideally, using more phantoms, using a more robust network. But until that happens, I think we're on our way. At least for daily dose accumulation monitoring, I think that's a lot easier to reach that goal. And it could definitely be used. I'd be very interested to see. Unfortunately, we didn't get enough time to apply any dosimetric analyses, like a gamma comparison between the CT and the various reconstruction methods. But ideally, in the future, that would be something that I'm looking into, and we will see how accurate that dose is.
Yeah, did you investigate how robust the model is on different CBCT modes, or would you have to train a new model for every?
You would have to, if you change any parameters, scanning parameters, you have to retrain it,
Yeah.
unfortunately, because there's different scatter conditions, different absorption physics happening, so you have to retrain it.
Thanks. Really nice work.
Thank you.
I just want to send a note to that. How dependent is that on the anatomical area?
Well,
Like a head or a large pelvis, small pelvis?
Interestingly enough, well, I investigated the head for this particular case. I would have to retrain it. Obviously, for pelvic scans, you use more MAS because there's more anatomy there. And so it had to be retrained. But in terms of the training stage, I use the pelvis phantom. And if I go back, okay, it's a lot. But including, so not using a pelvis phantom in SN4 resulted in a much higher reconstructed MAE. So even though the pelvis has no resemblance to the head in terms of its anatomy, the model was still taking those scatter conditions and learning how to, I guess, estimate the intensity deviations. So I was even thinking you could use watermelons or fruit, or it doesn't really matter as long as it's static between the CT and the CBCT. It can effectively be trained even in non-anthropomorphic phantoms.
Any questions from Zoom?
Yeah, I had one.
Yep.
So
This
given
is Brandon from
CBCT images, CBCT images are normally poor towards the edges of the images. Did you notice an increase in image quality towards the edge of the images compared to the centers of the images?
Not really. This is usually seen in pelvic acquisitions. I don't have the slide here. Where you get this like cupping artifact because of instabilities in the during the acquisition. But because I'm working on the head, it's small compared to the entire field of view of the CBCT acquisition. So I didn't really notice any of those particular non-uniformities across the image. And in general, yeah, there's just a lot of air region around the head, and so it's hard to see really if there's any artifacts there. There is a truncation artifact around, because I used RTK to reconstruct, so it's not a very sophisticated reconstruction. So sometimes there may be attenuation, there may be photons that are attenuated and measured by the detector, but if those attenuations occur outside of the reconstructed field of view, the algorithm doesn't know where to put them, so it accumulates around the edge. So you might see this like a ring that's present here. I've omitted some slides, but when I reconstructed the pelvis, it vastly exceeded the field of view, and you get these enormous kind of ring truncation artifacts. But thankfully for the head and neck scans, we don't get that because the field of view is larger than the head.
Thank you.
Any other questions from John? No? So one last comment maybe is a good application of your project. So for clinical CT, especially for kids, for the patients who are small patients or infants,
Mhm.
so dose is really important amount of dose.
Mm.
Do you think you can use your method, but use less dose,
Mm.
but improve the image quality, less dose and
Mm.
improve the image quality?
This is definitely an active area of research, and I did investigate this at the start. We did take with Mahsheed some low-dose measurements, but unfortunately, we decided to stick to the variant pathway, the standard clinical pathway, because that was what was being used in the hospital. But I did investigate briefly in the image domain, not in the projection domain, in the image domain, to correct for low-dose CBCT scans, and it worked okay. So there's a lot of potential in that.
Maybe a good potential for MTMP.
Yeah,
I got Phantom that you could use for that.
absolutely. Chuck it this way.
Any other project?